Okay, today we have a lot of things to learn, one of which is called dot product, one of which is you're going to find the angle between any two vectors, even if they're in 3D. And that is a kind of a complicated topic. So this one's not going to be super easy. We're going to start today with a little bit of review of yesterday, and hopefully you now get how to write things in column vector form or position vectors. All right, so for instance, if I wanted to just get right here, E, then notice these are labeled, this is the I direction, this is the J direction, and this is the K direction. So J is going this way, I is going that way, K is going up off the table, so to speak. Think of this as like this part right here is laying its surfaces on a table, and then it's going up off of the table. All right, so now here's my question. If I just wanted to get straight up there and the ray was that simple, sorry, the vector was that simple, you missed your chance. Too late, I already corrected. All right. So, hey, you missed, you guys were way too slow. I even caught myself before you caught me, so that's sad. Kind of have to work on that. Okay, so anyway, that vector right there has got a very simple directions to get there. You would go, for instance, how many eyes do I move? Start considering that's the origin right there. I move 0 in the I direction, plus how many J's do I move? 0 in the J direction, and then how many K's do I move? How do you know it's 5? If you read the problem, and it says each edge is 5. All right, so 5K. There we go. And then how could I write that as a column vector? It's simple. You just strip out the variables, and it's 0, 0, 5. That ring a bell? Do you remember doing that yesterday? Yes. I hear you. X, Y, and Z would make a lot of sense, but then that is just a position in space, and it isn't associated with vectors. Frankly, you could use any 3 letters you wanted to. Kind of the standard ones for vectors you'll find if you're looking out on the internet for videos on vectors and stuff. You'll see they'll use I, J, K. All right, so anyway, if you wanted to write this vector from O to G, you're going to have to go some in the I direction, some in the J direction, and some in the K direction to get to this spot right here, which is kind of like the dot you're headed towards. But remember, this isn't like polar. The answer isn't just a dot in space. It is the actual whole arrow that goes from here to there. All right. I'd like you to see if you can write that for me in both position vector and column vector style. Once you write it as a position vector, it's really not tough at all. Change that to column. All right, I'd like you to compare your answers, row 1 and 2. Compare with the person across from you. And if you say, I don't get it, then they're supposed to help you at that point. Row 3 and 4, rows 5 and 6. Okay, I heard a student explaining it, and I kind of like the way they said it. If you were going to go there, you'd have to go down here, and then you'd have to go up here, and then you'd have to go, and I'm going to say these words, off the table in this direction, up there. Okay, and that gets me to that spot kind of the long way, but it's still going to give me the answer, and that was 5 I's, 5 J's, and 5 K's, so it's 5I plus 5J plus 5K. Raise your hand if you had that one right. Good. And then, of course, it's just column with 3 5's in it. 5 over 5 over 5. That's the column vector for it. Are we good so far? How many of you feel like you're with me? You get this. Okay, good. Then BD is going to blow your mind. It's over there. It's not at the origin. How on earth are you going to say it? You You can't just say, well, I'm going to go over 5 i's and then up. You got to get it to be in a different place. Who's got an idea? What should I do? Yes, sir? Exactly. You are allowed to move it over because do you get if I go here, it's the same exact vector? Same magnitude, same direction, right? Okay, so tell me what to do. Move it to AE. You are warm. That does show you how far over and up, but it's from the wrong place. Yes, sir? I can't turn it, otherwise I'll be changing its direction. Yes, sir? Oh, you guys are all centered on the O, which is right, but you're not saying it right. Yes? The butt end, we call it the tail end. Yes? 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 Yes. Now, you can say how far over and how far down and then how far up. There's 3 directions to get to this spot. Now, I know that that's kind of hard to envision, but this kind of gave us a real good idea. Do you get it moves in the left-right direction, which is called I? Do you get it has to move in the I direction? Do you get it has to move up off the table? That's the K direction. Which direction does it not move in? J. There's no J's. Okay, so now we can move it to here, and we can get this answer by saying, okay, it's got to move left, and then it's got to move, it's not going to move any in that direction, but it is going to move up like that, and so what's the final answer? 5i? No, it didn't move 5 to the right. Negative 5i. It moved to the left from here. It moved that way. Yeah, that would matter. Okay, keep going. Oh, wait, you're going to do a different way, I think. But just give me the rest of the answer to this first. 0j plus 5k. Go on. Can't you just treat every spot like the origin? Yes, you can. But you'd have to understand, like, if you move it back here and act like the butt end, the tail end, is at the origin, then do you get you're moving left in the I direction, so therefore it's still negative? And then from there, you're moving not at all in that direction, so 0 in the J direction. And you are moving in the K direction, so yeah, you can do it that way. And there's an even better way. Who's got a different way? At least it may not be better, but different. Do you have a different way, or do you have a question? Can't tell. Okay, go ahead. Yes, it needs to be I, then J, then K. Because if you just write numbers randomly, do you get how you can't really tell which direction you're being told to move? To reiterate, you have to put them in the same order every time. So if you're going to have one that's skipped, you'd have to put a 0 for it. So you always have to tell me your I's, and then your J's, and then your K's. And in column vector form, you can't just put any number anywhere, right? So in the column vector form follows from the position vector form. So yeah, it always has to be I, then J, then K. And then in columns, it'll be the I is top, the J is in the middle, K is at the bottom. Yes? Good question. It's better to have it in there, but I would not mark it wrong if you didn't have that. But you're going to be then tempted to write the column vector wrong. You're going to be tempted if you didn't have the 0j. Do you get how you'd think, oh, I can just write negative 5 over 5? So it's better to have it in there so that you'll remember it's negative 5, 0, 5. Otherwise, your equations will get messed up. Okay, so let me show you the other way. That's pretty powerful. What's the name for that point? But what's its place? What's its vector that goes to that spot called? Could you hit the door for us, please? Okay. So that's how far over and how far up. And so in other words, what's its position vector called? 5, 5, 0. That's for B. Okay. How about D? 0, and then 5 in this direction, and 5, 0, 5, 5. All right. Anyone want to take a guess what I'm about to do? Yes? Subtract. So what minus what? It's important because if you do it backwards, you'll have the vector going the wrong way. It's the head minus the tail. This is the head end. That's the tail end down there. So it's 0 minus the 5, 5 minus 5, and 5 minus 0. 0 minus 5 is negative 5. 5 minus 5 is 0. 5 minus 0 is 5. Does that look kind of like that? All right. So what that's doing is moving, just like we did, moving the tail end of this vector over to there and telling you what the coordinates of the answer would be, which is negative 5 in the I direction, 0 in the J direction, and 5 in the K direction. There we go. There's your answer as a column vector, and I got it by taking this minus that. Head minus tail. I'd like you to write this head minus tail, head minus tail, and head minus tail as a way to remind yourself. If you write it down, you increase your chances of remembering it dramatically. Head minus tail, head minus tail, head minus tail. Now, I'd like you to actually do that to figure out the answer to EB. That's the third one up here. There's A, B, and C. I want you to figure out EB's answer by figuring out that's position vector. That would go from here to here. And then this one's position vector. And remember, it's going from the E to the B. The B is the head end. That's got a column vector. That's got a column vector. First, can we all agree that E's not moving in the I direction, not moving in the J direction, and only moving in the K direction, and it goes up? How far is that? 5. 0, 0, 5. Raise your hand if you had that right. Okay, good. Then the other spot is the head end. And then the head end, it moves 5 in this direction and 5 in that direction, but it doesn't go off the table. 5, 5, 0. Raise your hand if you had that right. Then when you subtract, from always do which one first? Head. Head minus tail. So 5 minus 0 is 5. This 5 minus this 0 is 5. And then 0 minus 5 is, there's your answer for EB. 5, 5, negative 5. Or if you wanted to write it out as position vector, it'd be 5i plus 5j minus 5k. Okay, so the moral of the story, you can do it by grabbing the vector and moving it, but there's a good way to do it without all that drawing, because some of you aren't that good at the drawing, frankly. So if you don't want to try to go, okay, where's that pointing to? And, oh, wait a minute, it's going down, isn't it? Which is kind of negative, and that can be really confusing, and it's actually relatively easy on a smartboard compared to just on paper, and so you might want to get good at just taking the column vectors and subtracting them. Okay, good. Next topic is a equation. I want you to see if you can put your mind around this equation. You've got U is this little vector, V is this little vector, and then they want you to add them here. I would recommend you add them as column vectors. So what's the column vector for this? Say it, it's quick. 3, 5, and this one, 1, negative 2. Good, and then add them, and what do you get? 4, 3. But I don't know A, and that's the point. Find A and B. So I don't know A, but it's being multiplied by U plus V, which was what again? 4, 3. What just happened there? Finish the equation, and you'll get a little equation out of it that you can solve for A. And once you know A, there's another little equation in it, and you can solve for B. Now, this next part might mess you up. To me, this was not super intuitive, easy, but for some kids, they just saw it. Oh, it's this over this. Let's see which one you are. And frankly, if you don't see it, totally okay. I'll talk you through it. I think you'll see it then. Okay, so what's this top thing? What is that for? It's 4 in the I direction, right? What's this 3 down here? 3 in the J direction. So we've already got our column as I and J. Now that you think of it that way, what should this spot be and what should that spot be? 8 in the I direction. And how far in the other direction? B minus 2. Now, some people might like this explanation, that this is 8 times I is technically 1 in this direction and 0 in that direction, which makes it 8 times 1, 0, which makes it 8, 0, plus B minus 2 in the J direction, which is 0 in that direction and 1 in that direction. When you do that, you get 8 times the 1 is an 8 on top, and in the other part, you'll get a B minus 2, not on the top because it's timesing by 0. You'll get it on the bottom. And when you actually add them, you'll get 8 over B minus 2. Now, some of you are just going to like it better to say, well, this is where the I's are supposed to go, and this is where the J's are supposed to go. But anyway, now that I got it written this way, could you... This is like a type of problem. Could you solve this type of problem? Give me a little equation now. Well, you have a question, don't you? Go ahead. Good question. To solve this, are you going to divide the 4, 3 off of the A? Kind of, but I would prefer it if you just write me a simple equation from it, because I think if we can just make a simple little multiply problem out of this, 4A is equal to 8. Isn't that like pretty easy to solve? Okay, so the other way might work, but this way I know will work. A times 3 is 3A equals B minus 2. There's 2 equations. This one's really easy to solve. So what's A? A is 2. Stick a 2 in there. Do you think it'd be easy to solve for B then? All right. So if that's 3 times 2 is 6, it's 6 equals B minus 2. Add 2 to both sides. B must equal 8. Those are scalars, so that this little equation they had would work. Okay, so that's solving equations based on vectors. Another topic mastered, hopefully. All right, this next one, oh, this is just a reminder that we need to grade. So I'm going to pause for a second while we grade the homework. So now we are into the new stuff. This is graphing vectors. Nah, nothing new there. But writing them as a unit vector and then using that to be able to say, I want the same vector, but you can't say like, but I want it 3 times longer. Instead, it'll be like, I want the same vector, but I want its length to be 17. Its magnitude. I'll show you how to do that with what's called a unit vector. And then we can find the angle between any 2 vectors, even in 3 dimensions. It's not that hard to find an angle between, let's say, this and another vector that's over here. I mean, that's just an angle. That's not hard to find. But when you add in the element of, oh, and it's got a third dimension, it's popping out towards you. It's hard to even like imagine that. That's coming towards you a little bit. Then that changes the angle to be challenging to find. But we've got a formula for that, and that's what I'm going to teach you how to do today. All right. So the first thing is you should have already, and if you're going to get behind here, this is not going to be pleasant. Stay caught up. So over 5 and down 3, that means this is down 3 and that's over 5. And then this would have a length, and this is something we haven't messed with very much, called the magnitude. Do you get how it's just the square root of 25 and 9? Let's make square root of 34. Raise your hand if you already had that. Okay, so good. Write it down now. Then find me the length of the other one. The magnitude of the other vector that we have. The other vector is over 2, up 1. So it's like that. Okay, did you see that that one had 2 on this side and 1 on that side? Actually, technically -2 and +1, but then when you square root 2 squared and 1 squared is 4 and 1 is 5, you get square root of 5. Raise your hand if you had square root of 5 this time. Okay, good. Then you found the magnitudes of your little vectors. Do you get the magnitudes? It's just square root of that squared plus that squared. Always will be. It's really that easy. Okay, good. So that's magnitude. So what the heck is a unit vector? It is a vector that's in the same direction as the original vector, but not the square root of 34 long. It's exactly 1 long. That's what unit means. The unit circle had a radius of 1. Okay, the unit vector before were the little vectors that went up and to the left, and they were exactly 1 long. This is in this unusual direction right here, but it's not about 6 long. Why do I say it's about 6 long? Square root of 36 would have been 6. It's a little less than 6, so it's like 5.9 or something like maybe 5.8 long. But I want it to be only 1 long. And why would this be handy? Because then once I find the unit vector and I want the answer to be, give me a vector that's the same exact direction but has a length of or a magnitude of 17, I will just be able to say 17 times this guy. 17 times the unit vector. If a unit vector has a magnitude of 1, I just got times it by 17. All right, so it'll be 17. It doesn't always 17, but whatever, however long you want it to be, times the unit vector. What the heck is the unit vector then? Well, the unit vector is take the normal vector, which was for A, I'm going to have you write this in position vector form, 5i minus 3j. Does that ring a bell? That's just the same exact thing as the column vector that I have for it here, but we usually write these in position vector form. But now I got to shrink it to be less than it was for its magnitude. Its magnitude was the square root of 34. How do I shrink that down to be 1? Well, I'm going to give you a hint. What if it was 8 units long? How would I shrink it down to be 1? Multiply by 1/8. If it had been 8 units long, you'd multiply by 1/8. So, not divide by, multiply by 1 over square root of 34. That is the unit vector. Done. That's it. You're going to multiply by 1 over. You can't divide vectors, you don't divide vectors. So, all right, so next we're going to have, would you agree that this is the exact same thing in column vector format? Just so you know, it could be like that, but again, there's reason why I'm suggesting position vectors are better in this case. But That's the same thing in column vector form. That's the unit vector. So let's say I wanted it to be a magnitude of 12. Times by 12. And couldn't the 12 really just jump right up onto here? 1 times 12. Yep. All right. Given that you saw how I did that one, and again, I'm fine with you just leaving the 12 out in front like that because I like that shows you know it's 12 times the unit vector. Okay. I'd like you to figure out the unit vector for B. That's that little hat. They actually, the way to say that correctly is B hat, according to the all-powerful Wikipedia. B hat. I'm asking you to do B hat now. My point is, you're doing this one. The little thingy is called hat. Yes. A hat. Okay. B hat. All right. So I'd like you, please don't get distracted by that. I'd like you to find this little part that's 1 over something times something. Figure out the unit vector for B hat. And then I'm going to tell you a typical question you'd be asked in the test. I'd like a vector in the same direction as B, but I want its magnitude to be 900. Such a large number. That changes everything. So first find the unit vector, then figure out the answer for me for my vector that's the same direction but 900 units in magnitude. Okay, unit vector. Not done yet. I don't think you really understand it. It's 1 over the magnitude of the original, root 5. And then I just say what the position vector is that we're talking about, which is negative 2i plus, I could write 1, or just write j. Raise your hand if you had that one right. Okay, cool. Now, to make that 900 long, I go 900 times the unit vector. Same exact thing as I had before. 1 over root 5, except I'm going to shortcut this one and put negative 2, 1. But you could have said negative 2i plus j. Just want you to know that both would be okay. Yes? Yes, you can move the 900 to the spot where the 1 is. It is okay to put that there. Okay. That is a kind of problem, and we're done with that kind of problem. Don't think that that's somehow related to find the angle. To find the angle, you don't use the hat things at all. That's the unit vectors, and they're for like, I want a vector that's 75 long going this way. That's how you do it with unit vectors. Okay, so done with that part, and now here's the last part. Find the angle between them. Would you agree the red one and the black one that are up here, the angle between them, you could kind of argue that you could go around the outside or you could go on the inside. Like you could have the angle that goes this way between them, or you could have the angle that goes that way between them. This is always going to figure out the angle for you that will be less than 180. You know what I mean? There's always one of those two that's less than 180, unless it actually is 180. Okay? All right. So, given that, what's the angle between them? Well, there's a formula for it, and it involves something called a dot product. So I need to teach you what a dot product is first. All right. I'm not going to derive it for you, given how much time we have left today. I'm just going to jump right to it. But the dot product for A and B looks just like you would think. It's got a dot between them. A dot B. Sadly, that is often mistaken for multiply by kids. That is a dot for a dot product, which is different than just multiplying them. All right? If the dot product of them will equal the magnitudes of them. Remember, this bars mean at magnitude of. The magnitude of the A vector times the magnitude of the B vector, and this, the dot is not a dot product because they are magnitudes. You just multiplying the two magnitudes, and that's multiplied by cosine of the angle. So to solve this thing, you never know the angle. So how do you solve for an angle? You use a calculator and type what button? Inverse cosine. Okay, so we'll use inverse cosine at the end of this puppy. All right. Which part don't we know? We won't know the angle until we've used our calculator. But we do know these guys. They're just the magnitudes. So the only part you really need to figure out how to do, by the way, the magnitudes are right here and right here. Root 5 and root 34. And it won't matter which one's which because I'm multiplying them anyway. Yes? Okay, just to clarify, not 1 over root 34, but root 34. Because the 1 over root 34 is meant... Oh, okay, well, it depends on the problem. Okay, if they ask... First of all, we don't blend these two together. But if you had this and this was your vector, you'd have to use that. But right now, I'm just going back to the original, which was the original A and B. So right here. That's the A vector. That's the B vector. We're not using these. Those were example problems of how you'd use unit vectors. Okay, I said something before that everybody's forgetting I said this part we're done with. Everything above the pink line, that's not a part of this. Everything below the pink line, that's not part of this. Not at all. Okay? Now what we're doing is a completely different question. Doesn't have to do with the 900 anything. This has to do with A and, okay, undo that, hold on. This has to do with A and B here. Okay? So I'm finding the dot product of A and B now. How do you do a dot product? It is extremely simple. You multiply the x's, you multiply the y's. Is there still x's in this? Yes, there is. That's the x amount of j, no, I, sorry. And this is the x amount of, or the y amount of j. So yeah, they're still called x's and y's. Those little parentheses that are drawn in, I can't here. I'll use my surgical eraser. Very small, little, careful eraser. There we go. Okay. So, what's the dot product? Multiply 5 and negative 2. What do you get? Negative 10. Multiply negative 3 and 1. What do you get? Negative 3. What's negative 10 and negative 3? You'd think maybe you might multiply them, but you don't. You add them at the end. So we had negative 10 for this part, and negative 3 for that part makes negative 13. That's your dot product. Negative 13 equals, what's the magnitude of A? Back to this is vector A right there. What's its magnitude? Square root 34. What's the magnitude of B? Square root of 5. And then cosine theta. And I'm almost done. I just got to get the cosine theta alone so that I can do inverse cosine to it. So I'm going to divide both sides by root 34 root 5. Root 34 root 5 cancels. Cosine is equal to that. So how do I fix it so I get theta alone? Inverse cosine. And then inverse cosine cancels the cosine, and theta is equal to all that. Now, I'll warn you, some kids are going to answer like 174, and other kids are going to answer like 4.2. How could two kids who both typed it incorrectly on their calculator have such different answers? Radians versus degrees. It's about 174 degrees. Somebody get it on the calculator. Did you get 174, 175? What was it? 175? Closer to 175. 175 degrees. Do you get how that is almost 180 degrees? And look at our original picture. Does it look like they're about 180 degrees? Ish. Okay, so that's 175 degrees. And who's got it in radians? It wasn't radians. 3.06. Since radians are about 59 degrees, that's pretty close to the same thing. So just be careful. You're going to assume it's degrees. Just go, if I were you, I'd have my calculator in degrees, because when the answer pops up, you're going to assume it's degrees. Now, if you want to be a boss and always have yours in radians because you know your answers are coming out in radians, cool. That works, but I think you make more mistakes that way until you're in calculus. Next year in calculus, from the beginning of the year, they're going to encourage you to reset your calculator to be in radians all the time. If you ever want to get degrees, you have to type in a degree symbol. So if you want to do sine of 30, otherwise you'd be doing sine of 30 radians. Totally different, 30 degrees. All right, if you don't have parentheses around this, it might not go into your calculator right. The parentheses around the root 34, root 5 might be necessary, but I don't know. I understand. Did you hear what I just said? Okay, I'll say it again for you. I recommend these parentheses around that. Inverse cosine of negative, and did you use a negative sign or a minus sign? That's another thing that messes people up. If you have negative 13 divided by parentheses, root 34 times root 5. All right, I am going to pause for just a second here. All right, so now I am going to set you loose on a problem to see if you understand this. Here's your two vectors, 2, negative 5, and 3, 8. This is going to be no, I is not a good choice. V and Q. And I would like you to find me the angle that would be between them by doing that little process we just did. Pause for a second and see if you can do it yet. All right, so here we go. You got to do the dot product of these two because that's on the left side. And that would be 2 times 3 is 6 plus negative 5 times 8 is negative 40. Did you get negative 34 for the dot product? Okay, good. Equals, and then the other side was the magnitude of this one, which is the square root of 2 squared and 5 squared, which is 25, and 4 squared of 29. Is that correct? Yeah. Then the dot product, and this is magnitude of. This is not a dot product, sorry. This is multiply by the other magnitude, which is square root of, help me, square root of 70 what? 73, thank you. Then you do cosine of theta, so in the end you do inverse cosine of negative 34 over root 29 root 73. And who had that? Okay, good. And what was it? Awesome. So wherever these two things were in two-dimensional space, it's not too tough to imagine, but if they were 3D, do you get the process would have been identical? Oh, wait a minute, you say. What if there was a 3 here and like a 1 there, and all of a sudden it's in 3D? The dot product would be just extended by one more thing. That's easy. How about the square roots? Can you find the square root of something that's in 3D space like that? Absolutely. It's the square root of all 3 of them added up. So the square root of not just x squared plus y squared, it's, in this case, it would be like 2 squared plus negative 5 squared plus 3 squared. And it's the square root of all 3 of them added up. So it really just flows kind of naturally, and actually, and it works. Yes? That's how you find the length of a 3D vector. Yep. Instead of a squared plus b squared equals c squared. Now, it's square, well, think of it this way. The answer to that is square root of a squared plus b squared is equal to c squared, or this is equal to c, right? So then if you had 3 dimensions, you're just going to have to throw in one more here. And now whatever you want to call your other thing, instead of c, let's call it m. M is equal to the square root of a squared plus b squared plus b squared. You can find the length of a 4-dimensional line, except it really won't mean anything. we can add a fourth dimension to it really easy. That's one of the things these scale up so easy. I'm going to say, okay, so let's put a 0 here and a 2 there, and all of a sudden you've got a 4-dimensional thing. We don't really know what it means, but all right. So that's the two major topics for the day were the little hat thing. What was the little hat thing called again? A what vector? A unit vector. And you can use that to find something, oh, I want the same direction, but 17 units long. And then this thing, which was the angle between two vectors. All right, listen close. I know we're almost done, but you have some homework. And I'm going to show you which ones you can skip. There it is. It's this on this yellow page. All right. The first one, you can skip the whole first page. Number 2 here with the hands, you can skip this one, the last one on this page. Okay. Next, I do want you to do this top word problem and this bottom word problem. The bottom word problem is where it wants it to have a vector of length 3 units. Do you get how we're going to do that whole multiply by the unit vector thing for this? All right. So do those 2 problems with the rope on the page. Problem 5 is good and not too tough, and it's got an equation. Remember how we solved an equation once in this hour? All right. And then number 6 is a skip. So you may skip number 6. Then move on to this should be 7 and 8. This is where you actually are finding the angle between the 2 lines, but they start with the dot product. Okay, so basically dot products, do both of them, and I'm just going to have you do one of those angle problems. The first one on this last page right there, you may skip that one, and that one. Okay, that's all I got for you for today. You can always fast forward to the end if you want to see what your homework was, if you go back and watch the video for today.